Hello, everyone. Today I want to talk about lasers and photonics, and in particular, PALTEC, which stands for Photonics and Laser Technical Education Center. So that center was established at Westchester Community College by a grant, NSF grant 1700564. It established a photonics concentration in our Mechanical Technology Associate's degree, but the classes can be used as electives in both the mechanical technology degree and the electrical technology degree. It's there to train students to work in this high-tech and high-demand field. The average starting salary in photonics with an associate's degree is over $47,000 a year. And within a few years, most people are making well above that. The reason that we pursued this was because the expected demand is over 4,000 jobs in the next 5 years in our area. So as part of this program, this grant, we modified three existing classes and started offering the modified classes in fall of 2018. The three classes that were modified were this class, our Intro to Tech class, our College Algebra with Trig class, and our Tech Physics class. Along with the modified classes, we developed two new classes, the first one being Fundamentals of Light and Lasers, and the second class being Laser and Laser Systems. And the Fundamentals of Light and Lasers was first offered in the fall of 2019. I'm going to ask that everyone in this class consider registering for it in the spring of 2020. We originally planned to run Fundamentals of Light and Lasers in the fall and Laser Systems in the spring, but due to the pandemic, we moved Fundamentals of Light and Lasers to the spring this year, and I have made arrangements that each student will get a kit that will allow them to do all of the labs at home, since again, we will be remote this spring. So when we set up this program, we've done it in a way that will connect the students, you guys, to the outside world with partners that we have, and also, it'll help you guys in getting this degree. But as we look at this in the classroom, which will be remote this spring, again, we have industry-aligned curriculum. It says motivated and experienced instructors. I will be teaching that class, and I actually have a New York State laser license that I got issued to me in 1978. So I think I have been working with these things for quite some time. We will be dealing with problem-based learning, with real industry examples, collaborative learning experience, and teamwork projects. You'll be able to gain skills that will allow you to serve to your community. Now, we will be working with other schools also when we deal with this, because we're getting equipment from other schools to help with now during the pandemic. So you will have, I mentioned we have partners. We'll have direct connection with industry experts. We normally bring guest speakers in, but I will try to do that via Zoom next semester. Again, with field trips will not be done next semester unless later in the semester I'm allowed to do that. But there is such a high demand that I feel very strongly that everybody who has any little interest should sign up and register for our Fundamentals in Light and Lasers class for this spring. And again, photonics is basically the cutting edge use of lasers, optics, fiber optics, optical devices. Starting salaries with an associate's degree are listed as $47,000 a year and go up from there. So what is photonics? Photonics is the science of light and photon generation, detection, and manipulation. I have the link in here, but as I found out, I can't really go to a YouTube video in these presentations, so I will also put this link separately on Blackboard and ask that you follow it. And then also I will be putting in a video that talks about our program directly, and I would ask that you please watch that video. And photonics are used in almost every field. So I'll start by talking a little about lasers. And a laser is a device that emits light through a process of optical amplification based on the stimulated emission of electromagnetic radiation. That's a little bit of a mouthful, but I'm going to talk a little more about that in a few minutes. The first laser was built in 1960 by Theodore Maiman at Hughes Research Laboratories. So laser itself is an acronym for light amplification by stimulated emission of radiation. So where are lasers used? And I start off with CDs, DVDs, and Blu-rays, even though those are sort of on their way out, as many of us are streaming videos and music, but they are still an optical medium that rely on a laser to play music or play a video. Fiber optics, some of you may have a fiber optic internet and video service coming into your house. Verizon Fios is an example of that. But even the regular cable companies rely heavily on fiber optics to transmit data. Data transmission itself in computers, there are ways to transmit it through fiber optics, and some of the servers that we're using actually have fiber optic data connections instead of wires, so you don't have the losses that are associated with wires. And one of our partners is actually IBM Watson Research Center, and what they are doing is they are studying embedded lasers inside computer chips, microchips, to allow for faster transmission of data inside the chip. And they're relying on micro-sized lasers so that they can do this, because data travels faster by light than it does through a wire. And this is a way that they could speed up that data transmission. In medicine, there are several laser techniques that are available for a variety of things. Everything from surgery. I actually had laser eye surgery, and something that could not have been done 30, 40 years ago is now fairly commonplace. But lasers are also used for cutting and for pinpoint accuracy in medicine, as well as things like tattoo removal or hair removal, or even skin conditions rely heavily on using lasers nowadays. There's also, on the biomedical side, lasers are also used to measure very quickly in the medical field. Cell phones. Some cell phones, mine is one of them, actually use a laser to focus the camera on there. So, there are lasers that are used in cell phones. construction. In the construction industry, lasers are used in various forms, very often for levels, right? From everything from leveling a ceiling to leveling a floor to actually being used in a surveying process now. And then that brings us into use for measurements. They are available. They have laser tape measures, so to speak, available where you hold it on one side and you can measure the size of the room just by using the laser. And those tend to work by measuring how fast that reflection of that light comes back. And also in the way of measurements, the police use lasers to measure your speed now. Instead of radar, they're using lasers. It's harder to detect because it has to be line of sight if you're detecting it. And so just about everywhere around us is lasers. You know, another one that to me, I see it fairly often. If you go to a store, like a supermarket, or, you know, they use lasers to scan when you're paying at the cash register. They're no longer prices on the stuff. They're using lasers. So they're everywhere around us. So how does a laser work? So a laser works. This is a picture of the internals of a laser, and this is a gas laser. Some of the new lasers are solid state, but they work on a similar function. So I have my tube that's filled with the gas. I have a 100% mirror on the one side, and I have a partially mirrored surface on the other, and I have a flash tube. And what happens is that flash tube is flashing at a certain rate, and the one side is 100% reflective, the other side of that mirror is 90%. So when the energy hits the tube with the gas gets excited and electrons move into a higher energy orbit. And if you remember from physics, when those electrons drop back from their higher energy orbit to their normal state, they emit photons. And basically, those photons are bouncing back and forth inside that tube until there's enough light that they come out. Laser light is very different from other sources of light in that the light that is emitted from a laser is what's called coherent light. So spatial coherence allows a laser to be focused to a very tight spot. And this enables applications such as laser cutting and lithography. It also allows a laser beam to stay narrow over greater distances. This is called collimation, and it enables applications such as laser pointers and LiDAR. So you're probably all familiar with laser pointers, and I have one that I bring to class with me when I'm teaching in front, because if I'm walking around the class, I could point to the board with the laser pointer. And the thing, because of its very tight, narrow beam, even from across the room, it's a small beam. That's different from other light sources, because other light sources, actually, the beam expands the further away it goes. And I remember this as a kid when we used to go camping and we had our flashlights, and we would love to shine the bright flashlight up in the sky, and you could watch the beam get wider as it goes up in the sky. The other important part with a laser is that it emits light in a very narrow spectrum, and it allows them to emit a single color of light. So in reality, the reason that a Blu-ray is called a Blu-ray is that that laser emits a blue light, and that blue light allows, because of its shorter wavelength, allows a lot more information to be packed in the same space as opposed to another different laser source. And so if you think about like the difference between a CD, a DVD, and a Blu-ray, a CD can hold 720 megabytes of data, a DVD approximately 4.5, and a Blu-ray 25 gigabytes of data. So that's a big, there's a big difference there. They could also provide very short pulses of light, which allows us to use them to transmit information. So in a fiber optic cable, as I do those pulses, it actually is transmitting data down the line or information down the line. I have a video that will be on Blackboard, which I will talk about a little later on, where I'm transmitting music. So the other way that it differs is the fact that it's coherent and it's of the same wavelength. So visible light contains multiple wavelengths and is not coherent. So if you look at figure 1, you see that all the waves of light line up and they're, basically following each other. They're all one on top of the other and they line up. Whereas with the incoherent light, there's different wavelengths and they're in different spots, so they're not coherent. So the electromagnetic spectrum basically covers everything from our gamma rays to radio waves, but visible light is in there, and it's a very small range in there, right? And going from approximately the wavelength of a little less than 400 and the high 300 nanometers up to about 750 nanometers, going from our violet to our reds. And then there's also ultraviolet below the violet and infrared above the red. So when we describe the properties of light, we're going to look at 3 things, mainly the wavelength, the frequency, and the amplitude. So the wavelength is the distance between successive crests of a wave, especially points in a sound wave or electromagnetic wave. The frequency is the rate at which a vibration occurs, and that constitutes a wave either in a material, such as sound waves, or in an electromagnetic field, as in radio waves and light. And that's usually measured per second. The amplitude is the maximum extent of vibration or oscillation measured from the position of equilibrium. So I like to look at that as its height, is its amplitude. Its speed, right? Basically, the speed of light actually does vary in different materials based on its index of refraction. And one of the labs that we do in the Fundamentals of Light and Laser class actually has us figure out the speed of light in different materials based on this index of refraction. The index of refraction also tells us how much the light bends when it goes through a certain medium. So if you guys sign up for this class, it's actually a fun lab that we do with this using a prism, and we watch how the light bends, and you measure how the light bends. And the phase is the position of the waveform. Again, coherence, waves have a constant phase difference. And then polarization is something where our light waves are in one plane. You may be familiar with this polarization term because that is used in things like sunglasses, right? I know the sunglasses I have are polarized, and they are very popular for people who um, do things outdoors like water sports or winter sports, because it cuts down a lot on the glare as it's bounced off of um, water surface or snow and the like. Um, but our computer screens are also polarized, and it's interesting because I know somebody who thought their cell phone was broken. When they walked outside, they were looking at their phone and they said, I don't see anything. My phone must be broken. And then they realized that they had polarized sunglasses on, took off the sunglasses, and were able to see their screen perfectly. Um, so, and then also the light has energy to it, and it's given by this equation. Energy is equal to H times V, and that's actually a nu, I'm sorry, it's a Greek letter nu. H is Planck's constant, and nu is the frequency of light. So I mentioned polarization before, and in this top drawing, you could see that unpolarized light, basically it's bouncing in all directions. It has, I could have partially polarized light, which is in picture C, and then picture D, I have plane polarized light, and you notice that the light is, the rays are all lined up. And one of the things that we do when we use polarizing filters is they actually consist of very, very small slits cut into the filter so that the light could only go in aligned in a plane. So I mentioned my demonstration. Since we are not live, I have a video of the demonstration that is posted on Blackboard. Please watch it. It's actually a pretty cool, fun demonstration. And basically what I'm doing in the demonstration is I'm transmitting sound with a laser. And a sound source is attached to, in this case, a helium neon laser that has circuitry that changes the intensity of the light based on the sound input. The laser is pointed as a receiver that has a detector that's hooked up to an amplifier with a speaker, and the speaker will reproduce the sound. Since the laser light is coherent, the distance could be increased without a loss of signal. So the nice thing about this, and if I'm in person, and what I'll do is, because of, again, the laser light being coherent, I could increase the distance. So I will normally start the demonstration out on a table, and you'll see that I'm transmitting the music. But then after we do some, demonstrate that, and then see how when you cut the beam, the sound stops, I will go and I'll move the receiver to the other side of the room. And by doing that, you'll see that I'm still transmitting the music, the sound, across the room instead of just across one table. And what I have done, but I can't do it right now, is I've also gone and done it from transmit the sound from one roof of one building on campus to another roof of another building on campus, right? Because again, because of the light being coherent, I can increase that distance. So a place where this is used, sometimes fiber optics. I actually have a fiber optic connection in my receiver for my sound, and yes, it transmits sound using a laser through a fiber optic cable. I hope you enjoyed this short presentation, and I hope that you consider registering for our Fundamentals of Light and Laser class in the spring. It's a great class. It's a lot of fun, and it can be used as an elective for mechanical and electrical technology. Please consider registering for it, and please watch the other videos that are posted on Blackboard along with this one. Thank you very much.